Hello again. This is Math 2134 coming to you from the College of DuPage, and the title of this lecture is Absolute Extrema. And extrema are maximum and minimum on a closed interval. Be sure you're an active learner as you watch this video. By way of introduction, here's a graph. And this graph is the graph, these are years, a span of 64 years. And here we have plotted the average age of cars that are in use. So you see at the beginning of this time frame, 9 years was the average age of a car that was in use. But as time went on, it fluctuated. And we had times when it was when we were having relative maximum, and there's a relative maximum too. It's bigger than anything near it, and so the relative this is a relative maximum as well, and these are relative maximum, and there's a relative minimum. But over this time frame of 64 years, you see that we also have periods where this is really the lowest over that entire period at these two values, and the maximum happens at this endpoint. So we're seeking these absolute extrema, or the absolute minimum values and the absolute maximum values. Here's a precise definition. C, if f of c is bigger than or equal to f of x for all x in the domain of f, then f of c is called the absolute maximum value of f. Now I will ask you to find c and f of c, but that ordered pair is the maximum value. That's the biggest, highest point on the curve. If f of x is bigger than or equal to f of c for all x in the domain of f, then f of c is called the absolute minimum of f. So here is an absolute minimum. Here's an absolute maximum. Here's a function that has an absolute minimum and an absolute maximum. And here's a function that doesn't have either an absolute maximum or an absolute minimum. So you see, a lot of different cases are possible. Here's the theorem that tells us an important case when we have these and can find them. If a function f is continuous on a closed interval a, b, this means that both a and b are included in this interval, and this is a finite interval. Then f has both an absolute maximum value and an absolute minimum value, and those absolute maximum values and absolute minimum values are achieved on the closed interval AB. So there are numbers in between A and B, or perhaps at A and B, where f does achieve these values. Let's look at a interval A to B and look at some of the things that could happen. And we see that x1, x2, and x3, here is x1, and at x1 the first derivative is equal to 0, and we see that that is a relative minimum. Here we see another relative minimum, and here we see a critical number. Here the derivative is 0 again, but here we see the derivative doesn't exist because there's an abrupt change in direction, but we still call that a critical number. But in this case you can see that the absolute minimum occurs at one of these critical numbers, but the absolute maximum occurs at an endpoint. This example suggests this would be a procedure that we could use to follow that, and in fact this is the procedure you should follow. So to find the absolute extrema, that is the absolute maximum and the absolute minimum of a function on a closed interval, step 1, find the critical numbers of f that lie in the open interval. So we're going to take the first derivative and see where does it not exist. That's one kind of critical number. And also we're going to see when is it equal to 0, the first derivative. Then we're going to compute the value of f at each of those critical numbers found in step 1, and also compute the values of f at the endpoints, f of a and f of b. Step 3, the absolute maximum value and the absolute minimum value of f correspond to the largest and the smallest of these numbers that were found in step 2. So there's the recipe. Let's apply that to a problem. So here in example 1, we're to find the absolute extrema, that means the absolute maximum and the absolute minimum of the function capital F of x equal x squared, defined on the closed interval going from -1 to 2. So we're going from -1 to 2. Now, this is a continuous function because it's a polynomial, and it is on a closed interval, and so the theorem applies. So what we're going to do is then we're going to look at the derivative of capital F of x. The derivative of f of x equal x squared is, as you know, 2x. And this exists everywhere, so there are no critical numbers of the kind where when the first derivative doesn't exist. But there is a critical number because if I set this equal to 0, f of 2x is equal to 0, I solve and I find out that x is equal to 0. So you see I have to test x equal to 0, x equal to -1, and x equal to 2 in the function. So I plug those into the function and I get these numbers. I'm plugging these values into this function. So it follows that 0 is the absolute minimum, that's the lowest number that we see here, and 4 is the absolute maximum of f. And so the maximum is 4, and it happens when x is 2. And you see we get that 0, 0 is the minimum point on the graph, and 2, 4 is the maximum point on that graph on the interval from -1 to 2. Let's do another example. Here we're to find the absolute extrema, that is the absolute maximum and the absolute minimum of the function y equals f of x equal x cubed minus 2x minus 4x plus 4. And this is defined on the interval from 0 to 3, again the closed interval. Again, this is a polynomial, so it is continuous, and it's also when we take the derivative, we'll get another polynomial, and so there are no places where the first derivative doesn't exist. Let's begin doing that though. Let's take this derivative, and we will get f prime of x is 3x squared minus 4x minus 4. Again, this exists for all values, so there are no critical numbers of that kind where the first derivative doesn't exist. And then I'm going to factor this and set this equal to 0. Now this is equal to 0 when the first one is equal to 0, we will solve and get x is equal to minus 2/3. When the second is equal to 0, we'll find x is 2. But x equal minus 2/3 is outside of this interval, and so it's just like it doesn't exist, so we discard that from further consideration. But x equal 2 is in this interval, and so that's the sole critical number of f. Then we're going to evaluate f of x at the 3 point, at the 0 point, and at the 2 point. We get these numbers, and from these results we conclude that minus 4 is the absolute minimum value of f, and 4 is the absolute maximum value of f. And you can see that these happen at 0, 4, and 2, minus 4. And if you look at the picture, you can see 0, 4 is the highest point, and 2 minus 4 is the lowest point on that interval going from 0 to 3. Here's another example. We're to find the absolute maximum and absolute minimum values. This time we don't say extrema, we could have, of the function y equals f of x equal x to the 2/3 on the interval from -1 to 8. Now we start by taking the derivative. But this is the first time in the examples we've talked about when we take the first derivative of this. So this is going to be 2/3 x to the 2/3 minus 1 is -1/3. So this is going to be 2 over 3. And then this is x. We're moving this into the denominator, x to the 1/3. Now this is not defined at x equals 0. And since there's a 2 in the numerator, it does not equal to 0 for any x. So we have only one critical number, and that is 0. So we're going to look at the endpoints of the interval, -1 and 8, as well as the critical number that we found of 0, and evaluate the function at those places. And we conclude that the absolute minimum of f is 0 when x is 0. And the absolute maximum is going to be 4 when x is equal to 8. This is the picture, and you can see what happens. There's, again, the abrupt change in direction here. This is the first time that we see, but it demonstrates the point that we can have these critical numbers of the second kind. And they can end up being our actual solution. Life is a word problem, so this certainly applies to word problems. Here we want to maximize profits. So this company's total profit in dollars for manufacturing and selling X units of this product of loudspeaker is given by P of X is equal to this quadratic function. And notice that this is only true from 0, less than or equal to X, less than or equal to 20,000. So this is a closed interval. This is a polynomial, so it's a continuous function. So the question is, how many units of the loudspeaker must they produce to maximize their profits? Okay, so the same kind of deal. We're going to plug in 0 into the equation. We're going to plug in 20,000 into the equation, and we're going to try to find some critical numbers here. Now this is a polynomial, so it's continuous and differentiable. So I will take the first derivative of this. When I take the first derivative of this, I will get P prime of x is equal to minus 0.04x plus 3,000. This is a continuous function, and there is no places where it doesn't exist. So I'm just going to set this equal to 0. When I set this equal to 0, I will get x is 7,500. So we evaluate this at 0, 20,000, and 7,500. And when I do this, you can see that the maximum profit happens at 7,500. And so that is that's the maximum profit. And you can also see that there are two places, if they don't produce anything or if they produce 20,000, that those will be the minimums on those intervals. Actually, that's not true. 20,000 will be the minimum because I was looking at it wrong. That's the minimum value. That's the maximum. This is nothing there. Let's look at applied example 5. Now, this is a science or health biology kind of thing. The trachea, that's your windpipe basically, contraction during a cough. When a person coughs, the trachea, windpipe, contracts, allowing air to be expelled at a maximum velocity. This protects you from choking. It can be shown that when a cough, the velocity v of the airflow is given by the function v is equal to f of r. That's the radius of the windpipe, lowercase r, and that's equal to kr squared times capital R minus r, where r is the trachea's radius in centimeters during the cough, r is the tracheum's normal radius in centimeters, and k is a constant that depends on the length of the trachea. You define the value of lowercase r for which the velocity of airflow is the greatest. Now you see this r is a constant, the capital R, and the lowercase r is a variable. Okay, so what we're going to do is we're going to look at this and we're trying to maximize the velocity. So we're going to say, oh, this could run from 0 being the radius all the way to capital R being the radius. So you see we want to find the absolute maximum of f on the interval 0 to capital R. So what we're going to do is we're going to take the derivative of this. Now this causes us to use the product rule. So it's going to be the derivative of the first times the second minus the derivative of the second with respect to r times the first. And notice that we get, using the product rule, that is going to be minus kr squared. Okay, so we're going to simplify this, distribute and so on and so forth, and we notice that we can factor out kr. Now this is defined for all values of r, so we don't have those critical points of the second kind, but we will have a critical point where we set this equal to 0. Now this is equal to 0 in there are two times. One is when r is equal to 0, and the other time is when r is equal to 2/3 capital R. Now, r equals 0 doesn't really make a lot of sense in this problem, so 2/3 capital R is the sole critical point. F of r is an endpoint. So we evaluate this at 0, 2/3 r, and capital R. And we see that we get 0 there, but we get this number. Since capital R is positive, we see that this is the maximum. So this, we can deduce that the velocity of airflow is greatest when the radius of the contracted trachea is 2/3 of capital R. And here's the graph, and we can see what happens, and that indeed is an absolute maximum. Let's look at one talking about minimizing average cost. You remember that average cost is you take the cost function c of x, but you divide it all the way through by x. And so this is c bar of x, and notice that when I do that, I do get an x in the denominator. And so this is an average cost function, c bar, and x is bigger than 0 because you can't have x equal to 0. So what we want to do is show that a production level of 500 units per day results in a minimum average cost. Well, you really can go from 0 to infinity, and so to solve the problem, we're going to use a graphical method, and we're going to take the derivative. Now, when we take the derivative of this, x can't be 0, but when we take the derivative of this, we're going to get, and you should verify these calculations for yourself, 0.0002x minus 0.08, and this is going to be, this is 5,000 x to the minus 1, so this is going to be minus 5,000 over x squared. Now we're substituting the given value 500 into that, and we find out that that's equal to 0, so that is a critical number. And now we're going to use the second derivative test, which we've studied in a previous chapter, previous lecture. The second derivative is equal to this, and if we substitute this value in, we find that the second derivative is greater than 0. The second derivative greater than 0 means we're concave up. That means that this is a minimum because it's concave upward everywhere. And I mean, you can, if you take that derivative, you can see that it's greater than 0 everywhere, and so that means that's a minimum. Now the minimum average cost is found by taking that number of 500 and plugging it back into the equation, and we find out that $35 per unit is the average minimum cost. And you can see what happens here. The average cost, it costs you a lot to make just a few. It goes down, but then it starts costing you more and more. So the minimum happens at 500, 35. Here's an example from physics, and this is the flight of a rocket. The altitude in feet of a rocket, t seconds into its flight, is given by s, that's the altitude, is equal to f of t. It's a function of time. It's going to be minus t cubed plus 96t squared plus 5 for t greater than or equal to 0. We're to find the maximum altitude obtained by the rocket. So that means we want to find the maximum value of this function. So we're going to take the derivative of this function. So f prime of t is going to be equal to minus 3t squared plus 192t. And this is defined for all values, so the only critical numbers are going to happen when f prime of t is equal to 0. We factor this and we set it equal to 0. Well, we find out that either t is equal to 0 or t is equal to 64. So we're going to evaluate f at those critical values and the endpoints, and we'll get f of 0 is 5 and f of 64 is this big number. So this big number is going to be the maximum value of f, and that's going to be the maximum height, is 131,077. So that's the maximum height. And we also know from this that that happens when t is equal to 64. So it takes 64 seconds to reach its maximum height. Now the second question wants us to find the maximum velocity. Well, velocity is the first derivative, so you see this is the velocity function, And so this is, again, the velocity function for t greater than 0. But we want to maximize this now, the maximum velocity. So we're going to take the derivative of this. And when we do that, we will get minus 6t plus 192. This is defined for all values of t. So we're going to set that equal to 0, and we'll find that the critical number is going to be 32 when that's equal to 0. And since we know that the next derivative of this is minus 6, which is less than 0, that tells us by the second derivative test that this is concave down. It's like this. So that means this is where you're going to find that this is in fact going to be a maximum velocity. So it's going to be going 6, feet per second is going to be its maximum downward velocity. Excuse me, it's going to be equal to 0 when t is equal to 32. Here we're just finding this, and so that means its maximum velocity is going to be 3072 feet per second. I apologize for that. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. May God bless you all.